There may be secrets in the universe that even time itself cannot touch. The idea slips in quietly like a whisper in a darkened room, yet it lingers, unsettling and persistent. It is not the kind of question you can put away neatly on a shelf and forget about. Once you've heard it, it follows you into your thoughts, into your dreams, into the quiet moments when your mind wanders. What happens to information when it falls into a black hole? This is not just a matter of physics. It is in many ways a philosophical nightmare, a challenge to the very structure of reality as we think we understand it. For decades, scientists have wrestled with this question, pacing the fine line between what is known and what cannot yet be proven. It may sound abstract, something to be discussed over coffee in a university lounge or buried deep in a scientific journal, but it is far more than that. This single problem cuts into the heart of modern physics, connecting the grand equations that govern galaxies with the invisible threads that bind the smallest particles of matter. It asks whether the universe is a careful keeper of every story ever told, or if it is capable of letting those stories vanish without a trace. Imagine for a moment that the universe is a library, not a modest one with a few 100,000 volumes, but an infinite archive. In this library, every star, every planet, every moment of your life is written down in exquisite detail. The collapse of a sun, the trajectory of a comet, the sound of a laugh on a rainy afternoon, all recorded somewhere. The shelves stretch beyond sight, beyond comprehension, filled with books that no human hand could ever hold, but each one is real, containing the complete history of something that once existed. Now picture this: one day a book is taken from the shelf and hurled into the mouth of a black hole. You watch as it falls, drawn faster and faster toward the event horizon until it crosses that invisible boundary and is gone. You cannot follow it. No light, no signal, no message escapes. From where you stand, it is as if the book has ceased to exist. But has it? Are the words inside the details of the star, the planet, the moment still somewhere locked away in a place we cannot reach? Or are they gone, erased from the universe as if they had never been? This is the crux of the black hole. Information paradox, though we have not yet named it here. It is the quiet but unnerving thought that maybe reality is not as permanent as we like to think. You could destroy a chair, burn a photograph, smash a clock, and the laws of physics as we have always understood them say that the information about those objects, about their arrangement of particles, is not lost. It is scattered, changed, perhaps impossible to reconstruct, but it is still there. Nature keeps a record. Yet black holes challenge that idea in the most extreme way possible. The question becomes even more unsettling when you remember that black holes are not rare curiosities hiding at the far edges of the cosmos. They are here in our own galaxy. They lurk at the hearts of galaxies millions of light years away. Some are the size of a single city, others billions of times more massive than our sun. They consume stars, gas, even other black holes. And if they can make information disappear, then every time they feed, the universe itself loses part of its memory. Why should that matter to you? Because if information can truly be erased, then the rules we thought were unbreakable. The same rules that allow us to predict the motion of planets, the behavior of atoms, the unfolding of chemical reactions may not be rules at all, only guidelines. If the ledger of the universe can be rewritten, then the past is not fixed, and the future is less certain than we ever imagined. The foundations of science begin to wobble. There is also something deeply human in the fear of losing information. We tell stories to preserve what would otherwise fade. We build archives, write books, save photographs, not only to remember, but to resist the erosion of time. If the universe itself can forget, then what does that say about our own efforts to hold on? And what if the opposite is true? What if nothing is ever forgotten, and every detail of every life remains somewhere, no matter how deeply it is, buried? Which of those possibilities is more comforting? Which is more terrifying? I sometimes wonder, and you might too, whether we should be rooting for information to survive. If it does, then, in principle, somewhere in the structure of space-time is the complete record of you, me, everyone. Every word you've spoken, every decision you've made stored like an unbroken chain. To know that is to realize that nothing you have ever done is truly gone. But if information is lost, then there is a kind of mercy in forgetting. Mistakes, griefs, and regrets can vanish into the dark, never to be recovered. A black hole becomes not only a destroyer, but a kind of absolution. The scientists who lose sleep over this problem are not chasing an answer out of idle curiosity. They know that whichever way the truth falls, it will change the way we see reality itself. They speak of entropy and unitarity, of quantum mechanics and general relativity. But beneath the technical language is something primal. The need to know whether the universe plays fair, whether it follows its own rules or bends them when one is watching. Perhaps in some distant future, someone will find a way to peer past the event horizon, to listen in on what the black hole is holding back. Perhaps the whispers from the darkness will become a voice we can understand. Or perhaps we will never know, and that ignorance will be its own kind of truth. For now, the question remains. It hovers in the silence between what we can see and what we cannot, between what the equations promise and what they refuse to yield. Somewhere out there, a black hole is holding on to a secret. Whether it will ever let go is something no one can say. But to even begin answering, we must turn and face the creature itself, the silent, sightless thing at the heart of this mystery. And that means stepping closer to the edge than most are willing to go. There are predators out there that do not need eyes to see you. They do not stalk with the patience of a lion or the cunning of a wolf, and they do not announce their presence with a flash of teeth or a sudden lunge. They wait in perfect silence, hidden in plain sight, warping the space around them so that you never truly see them coming. The moment you cross a certain invisible threshold, you are theirs. No escape, no bargaining, no second chances. These are black holes, the universe's most merciless hunters. To call them holes is misleading. They are not empty spaces, not voids where nothing exists. A black hole is a thing, an object born from something once full of light and life. It begins with a star, a massive one, far larger than the sun that warms our Earth. For millions, sometimes billions of years, that star burns, fusing hydrogen into helium, into heavier elements generating light heat, and the delicate balance between gravity pulling inward and the star's own energy pushing outward. But nothing lasts forever. When a star of sufficient size runs out of fuel, that outward push fails. Gravity-patient, relentless gravity wins. The star collapses its core, imploding its outer layers, thrown into space in a supernova so bright it can outshine an entire galaxy for a brief moment. What is left behind is strange beyond imagination, a singularity, a point of infinite density where the known laws of physics can no longer be trusted. Around it lies the event horizon, the boundary from which nothing, not even light, can return. Once you cross it, you are cut off from the universe you came from. No message can be sent, no cry can be heard. From the outside, the fall seems to slow, as if time itself is resisting the plunge, but for you the journey ends in an instant. Black holes are not indiscriminate in the way a storm or a fire might be. They are patient and precise. They feed only when something strays too close, yet their influence reaches far. Their gravity bends light, distorting the stars behind them into eerie halos. It stretches time itself, slowing the ticking of clocks for anyone caught near their grip. You could orbit one at a safe distance for years, watching the universe outside race ahead while you age more slowly. In this way, they are not only predators, but also strange time machines bending reality to their will, without ever moving from their place. To scientists, black holes are more than cosmic threats. They are the ultimate laboratories, natural experiments in the most extreme conditions imaginable. Inside their pull, the fabric of space-time is twisted beyond anything we can recreate on Earth. The physics we know, Newton's, Einstein's, the delicate machinery of quantum mechanics all meet here, colliding in ways we do not yet fully understand. By studying black holes, we are not just peering into dangerous territory, we are confronting the very edges of our theories, the places where our most trusted ideas break apart. And yet, for all their danger, there is a strange beauty to them. Think of a black hole not as an absence, but as a presence so intense it becomes invisible. The stars that circle them, the glowing disks of superheated gas spiraling inwards, the jets of energy shooting out from their poles. All of these are signs of something immense and powerful. The black hole itself remains hidden, its form unknowable, but its presence undeniable. It is the shadow at the center of a whirlpool, the stillness inside a storm. In myth and story, we have always given form to the things that threaten us. We imagine monsters lurking in forests, demons in the dark creatures at the edge of the map. If black holes had been known to ancient storytellers, they might have been cast as ancient gods or beasts, lying in wait at the borders of the world, their hunger infinite, their patience eternal. But unlike those myths, black holes are real. They do not need our belief to exist. They have been here since the first generation of stars burned out, and they will remain long after our own sun has faded into cold ash. From a distance, they can seem almost serene. A black hole in the center of a galaxy may sit quietly for centuries, surrounded by stars that orbit it in a perfect, silent dance. Yet when something wanders too close, a cloud of gas, a star, even another black hole, that serenity shatters. The victim is stretched and torn apart, heated to incredible temperatures and swallowed whole. The process releases unimaginable amounts of energy, briefly making the black hole's surroundings the brightest place in the universe. But when the feast is over, the monster returns to its quiet watch, as if nothing had happened. It is easy to imagine black holes as rule breakers, simply because they defy so much of our intuition. But they are, in their own way, bound by the laws of nature, even if those laws are stranger than we ever expected. Their gravity follows the same equations as any other objects, only amplified to an extreme. Their formation follows from the same forces that shape stars and planets, only pushed to a breaking point. And yet there is one rule, one principle of physics so deeply embedded in our understanding of the universe that black holes seem determined to challenge it. That principle is the conservation of information. The idea that no matter what happens to matter or energy, the information about its original state is never truly lost. It can be scrambled, hidden, transformed beyond recognition, but it remains somewhere in the universe. And here is where the black hole becomes more than a predator, more than a strange object in the sky. Here is where it becomes a question mark at the heart of physics itself. Because if a black hole can destroy information, then it is not just breaking a rule, it is breaking the very foundation on which our understanding of reality rests. So we are left with an unsettling truth. The predator without eyes may be following the laws we know, or it may be quietly rewriting them when we are not looking. And if it can do that, then what else might be possible? What other certainties might collapse under their own weight, just as a star collapses into the darkness? To find out, we will have to go deeper. We will have to stop looking from a safe distance and start asking what really happens when the laws of nature themselves are put to the test at the edge of a black hole's event horizon. We will have to face the possibility that in the heart of the darkness, the rules we have trusted all along may not apply. And that means preparing to confront the one mystery black holes have been keeping since the beginning, a mystery that could change everything we think we know. In the universe, no sentence is ever erased, no page ever truly burned, no record completely wiped away. That is the promise written into the very fabric of reality, or at least that is what we thought until black holes came along and threatened to be the exception. For centuries, physics has been built on the belief that while matter and energy can change form, the information that describes them is indestructible. It can be hidden, tangled, or transformed into a shape no one recognizes, but it still exists somewhere. This is not just a philosophical nicety, it is one of the bedrock principles of quantum mechanics, the branch of physics that governs the tiniest building blocks of reality. Imagine every particle in the universe as carrying a unique signature, a subtle and precise description of what it is, where it has been, and how it moves. Smash a glass on the floor, and you might think the original object is gone. But if you could somehow track every shard, every speck of dust, every vibrating molecule of air set in motion by the impact, you could, in theory, reconstruct the moment it broke. That is the essence of the conservation of information. The universe, in a sense, keeps an unbroken ledger of every transaction that has ever happened. An infinite bookkeeping system that never closes its accounts. Quantum mechanics demands this rule be absolute. Particles may dance unpredictably, their positions and velocities clouded by uncertainty, but the total information describing them remains intact. This law is so fundamental that without it, much of modern physics collapses into chaos. Our ability to predict outcomes, to trust equations, to build technology, all of it depends on the belief that the universe is a perfect archivist. Now introduce a black hole into this tidy library of existence, and things get messy. When an object falls past the event horizon, it is as if it has been checked out by a patron who never returns. It never even sends a postcard to say it is safe. The information it contained, the precise arrangement of its particles, the unique fingerprint of its structure, vanishes from view. To an outside observer, it seems to disappear completely. And here lies the problem: if the black hole truly erases that information, it is committing a crime against the laws of physics themselves. This is where Stephen Hawking shook the world of science. In the 1972nd, Hawking combined Einstein's general relativity with quantum mechanics to make a startling prediction: black holes are not completely black. Instead, they emit a faint radiation, now known as Hawking radiation, which slowly saps their mass and energy. Over unimaginable timescales, a black hole will evaporate entirely. At first, this seemed like a triumph, a way for black holes to eventually release what they had taken in. But Hawking's calculations revealed a darker twist. The radiation did not seem to carry the original information back into the universe. It was random, stripped of the details that once described whatever had fallen in. When the black hole vanished, so too, it seemed, did the ledger entries of everything it had devoured. This was more than a technical issue. If Hawking was right, it meant the universe was not a perfect archivist after all. The cosmic library was not just losing books, it was shredding them, burning them, scattering their ashes to the wind, leaving no trace they had ever existed. This would not only break quantum mechanics, it would fracture the delicate bridge between quantum theory and general relativity, the two great pillars of modern physics. One of them would have to give, and no one wanted to admit which. For physicists, this information paradox was not just a problem to solve, it was a direct challenge to the coherence of reality. If information could vanish without a trace, then the universe could not be trusted to preserve its own history. Cause and effect would unravel. The past could no longer be fully connected to the future. Predictability, the very thing that makes science possible, would crumble. Some tried to argue that the information must be hidden somewhere, perhaps encoded in subtle patterns on the event horizon itself, or released in some form we had not yet discovered. Others sided with Hawking's grim conclusion, suggesting that the loss was real and that we would need a radical new physics to explain how the universe works without this sacred principle. The implications stretched far beyond black holes. If information could be destroyed here, what would stop it from being destroyed elsewhere? Would the arrow of time itself lose meaning? Would entropy, the gradual slide from order to disorder, be something even more mysterious than we thought? The questions piled up, and every possible answer seemed to carry its own catastrophe. The paradox also revealed something humbling. For all our advances, for all our spacecraft and particle accelerators and equations scribbled on chalkboards, there remain places in the universe where our understanding shatters. The edge of a black hole is not just a boundary in space, it is a boundary in knowledge. To cross it even in thought is to enter a realm where our most trusted rules no longer seem to apply. Hawking himself admitted the danger of his proposal. To say that information is lost forever is to say that one of the most beautiful and successful frameworks in science is incomplete, maybe even wrong. And yet he was willing to follow the mathematics wherever it led, no matter how unsettling the destination. That boldness, that refusal to protect a cherished law, simply because it was cherished, is part of what made him a legend. But what drove him to such a dangerous idea? Was it purely the logic of his equations, or did he see something deeper, a truth about the universe that others had missed? To understand why Hawking would risk toppling one of physics' most sacred laws, we must step back into the moment when his discovery began, into the strange marriage of gravity and quantum mechanics that birthed the paradox. And once we do, we will see just how fragile our picture of reality becomes when it is illuminated by the faint, ghostly glow of Hawking radiation. A black hole might be breathing, not in the way lungs draw in air, but with an almost imperceptible exhalation of energy, a whisper of existence that slips out into the cold vacuum of space. For decades, black holes were thought to be the ultimate sinkholes of reality, swallowing everything and giving nothing back. But Stephen Hawking's groundbreaking insight in the 1972nd shattered that image. Using the principles of quantum mechanics, he discovered that black holes are not completely black at all. Instead, they emit a faint, ghostly radiation, a kind of cosmic sigh, now known as Hawking radiation. To understand why, we have to peer into the quantum realm, a place where space is never truly empty. Even in the deepest vacuum, the quantum fabric of reality seethes with fluctuations. Pairs of particles and their mirror opposites, antiparticles, flicker into existence for the briefest moments before annihilating each other and vanishing again. This constant birth and death dance is not science fiction. It is a measurable consequence of the uncertainty principle, which forbids space from being perfectly still. Normally, this quantum froth remains hidden, a restless background hum beneath the stage of the universe. But near the event horizon of a black hole, the rules change. The horizon is the ultimate point of no return, where gravity's pull becomes so strong that even light cannot escape. If a virtual particle-antiparticle pair appears right at this edge, gravity can tear them apart before they have the chance to annihilate each other. One particle falls inward, swallowed by the black hole's grip, while the other escapes into space. From the perspective of an outside observer, that escaping particle is real, carrying away a tiny fraction of the black hole's energy. Over time, these escaped particles form a steady trickle of radiation. It is unimaginably faint, far beyond our current ability to detect from a real black hole. But in theory, it is always there, and it comes at a cost. To release energy is to lose mass, thanks to Einstein's equation E max squared. Every escaping photon or particle ever so slightly shrinks the black hole. Given enough eons longer than the current age of the universe for most black holes, this process would cause the black hole to lose all its mass and evaporate completely. This was a revelation. The monsters we thought were eternal could in fact die. The slow leak of Hawking radiation is their mortality, their final breath. But this discovery came with a problem that shook physics to its core. If the black hole disappears entirely, what happens to the information about everything it swallowed? Does it come back out, somehow encoded in the radiation? Or is it gone forever, erased from the universe? Hawking's original calculations suggested a troubling answer. The radiation was thermal, meaning it carried no information about what had fallen in. Whether the black hole had devoured a star, a planet, or an encyclopedia of Shakespeare's plays, the radiation escaping into the void would look exactly the same. When the black hole finally evaporated, there would be nothing left to tell the universe what had once been there. The ledger entries would be wiped clean. This was the spark that ignited the infamous information paradox. On one side stood the iron law of quantum mechanics, declaring that information can never be destroyed. On the other was Hawking's stark conclusion, which implied that black holes might be cosmic shredders, reducing history itself to untraceable ash. Both could not be right, yet each had the weight of decades of theory and evidence behind it. Physicists argued fiercely. Some believed the information must be hidden in the radiation itself, encoded in ways we had not yet learned to read, perhaps through subtle correlations between particles that appear random at first glance. Others proposed that the information clings to the event horizon in a thin, two-dimensional imprint, an idea that would later evolve into the holographic principle. Still others suggested that new physics beyond both quantum theory and general relativity would have to emerge to reconcile the conflict. But one thing was certain: Hawking radiation changed the way we saw black holes. No longer were they mere silent graveyards for matter and energy. They were dynamic, evolving entities, slowly evaporating over cosmic timescales. They could live age and die just like stars, though, on a timescale so vast that to human eyes they still appear eternal. The thought that something so powerful, so all-consuming could also be so fragile is oddly poetic. A black hole, for all its might, cannot escape the subtle pull of quantum law. Its end is not a violent explosion, but a quiet fading, a dimming ember in the darkness. And somewhere in that fading lies one of the greatest mysteries of modern science, whether the universe keeps its promises or whether some of its stories vanish without a trace. And so we are left with a question as delicate as the radiation itself. When the last breath escapes from a dying black hole, what is it truly carrying? Is it nothing but heat, or the encrypted memory of a cosmic past we can no longer recognize? That question is the heart of one of the most persistent and maddening paradoxes in physics. A puzzle that forces us to confront what we really mean when we say nothing is ever lost. Two pillars of physics are locked in open rebellion against each other. On one side stands general relativity, Einstein's towering masterpiece describing gravity as the curvature of space-time itself. On the other side, quantum mechanics, a strange but unfailingly accurate set of rules that governs the smallest building blocks of reality. For nearly a century, these two theories have reigned supreme in their own domains, each tested to staggering precision. Yet when you place them together inside a black hole, the peace treaty shatters. They cannot both be right. The trouble begins with Hawking's revelation. If black holes slowly radiate away their mass and eventually vanish, then whatever fell into them, stars, planets, even entire histories, seems to vanish as well. According to quantum mechanics, that's impossible. The laws of quantum physics insist that information is conserved no matter how violently matter is transformed. Smash an atom to pieces, burn a book to ashes, even detonate a planet. In principle, the details of its original structure are still woven into the fabric of the universe. You could in theory reconstruct them if you had the patience, the precision, and a laboratory the size of infinity. But Hawking's calculations painted a colder, starker picture. The radiation escaping a black hole was purely thermal, random, and memoryless. It told you nothing about what was inside. If you believed this, then when the black hole's final whisper of energy faded into the void, the information about its contents would be gone forever, not scrambled, not hidden, but annihilated. General relativity, for its part, did not seem to mind the loss. In Einstein's smooth, continuous spacetime, once something passes the event horizon, it is simply gone from the outside world. The mathematics says nothing about the fate of its details, and it has no mechanism for returning them. But quantum mechanics rebels. To erase information is to shatter its most sacred principle. If Hawking was correct, then quantum theory, the foundation of everything from particle physics to semiconductor electronics, would be wrong. Physicists now faced a grim choice. Either one of their most trusted theories was flawed, or the very concept of information in the universe needed to be rewritten. The paradox carved a jagged crack into the wall of physics, a place where neither Einstein's elegant geometry nor the probabilistic dance of quantum fields could pass unscathed. This was not just a technical quibble over equations. It was a sign that we had reached the edge of our understanding, a fault line hinting that our picture of reality might be missing a vital piece. Imagine finding an ancient map of the Earth, perfectly accurate in most places, but with one enormous region marked "Here be dragons." The black hole information paradox is that uncharted territory, and somewhere in its depths lies the truth about how the universe really works. Some took the paradox as a call to arms. Perhaps they argued, information isn't destroyed at all. Maybe it escapes encoded in the Hawking radiation, so subtly hidden in correlations between particles that our current methods can't detect it. Others suggested the information is stored at the event horizon itself, etched onto a two-dimensional surface like a cosmic hologram, an idea that would later inspire revolutionary thinking about the universe as a whole. But even these proposals face trouble. General relativity demands that anything crossing the horizon experiences nothing special at all. The infalling astronaut, for example, should drift past without drama until tidal forces eventually tear them apart deeper inside. Yet storing information at the horizon seems to require some kind of invisible firewall, a violent boundary that burns away matter the instant it tries to enter. This firewall, if real, would directly contradict relativity's smooth, unbroken spacetime. In other words, trying to save quantum mechanics might mean breaking Einstein's picture of the universe. Trying to save Einstein's picture might mean breaking quantum mechanics. It was like a cosmic tug-of-war, where the rope was made of the laws of reality itself, and neither side could afford to lose. The stakes went far beyond black holes. If information could truly be destroyed, then predictability itself would crumble. The universe would be more like a chaotic dream, where the past can be erased without trace, where cause and effect lose their anchor. Science depends on the assumption that in principle the state of the universe now contains everything needed to know its past and predict its future. Break that, and the entire scientific method begins to wobble. This is why the information paradox is one of the deepest puzzles in all of physics. It is not just about the fate of a few unlucky stars or the workings of a distant singularity. It is about the integrity of the universe's story. Does the cosmos keep a perfect record of its own history, or are there pages that can be torn out and burned without leaving even a hint of ash? And so the paradox stands stubborn and immovable. On one side, the curved spacetime of Einstein's vision, majestic and continuous, caring nothing for the tiny details of quantum information. On the other, the jittery probabilistic laws of quantum theory, fiercely guarding the permanence of data as if it were the soul of the universe. In the space between them lies a gap we cannot yet bridge, a riddle that refuses to be solved. One of the first proposed answers would sound as if it had stepped straight out of the pages of science fiction, and in a way that's exactly where some of the most daring ideas in physics are born. Imagine standing at the edge of a black hole staring at the invisible frontier, known as the event horizon, a surface beyond which nothing can return. Common sense says that whatever crosses, it falls inward, plunging toward the singularity at the center, forever hidden from the outside universe. But what if that intuition is wrong? What if nothing truly disappears inside, at least not in the way we imagine? Some physicists have suggested that the information about everything that has ever fallen into a black hole doesn't vanish into its depths, but instead remains right there on the surface, clinging to the event horizon like an invisible tattoo. This is the essence of a radical idea. The event horizon is not just a passive boundary, but an active storage device, a kind of cosmic skin, capable of holding the blueprint of everything that has crossed it. From a distance you might think you are watching matter tumble inward, but in the deepest mathematical sense the story is different. The object's three-dimensional reality is smeared, stretched, and recorded on a two-dimensional shell. To make sense of this, imagine a snow globe. Inside, a miniature world exists in 3 dimensions. Now imagine that every detail of that world, every building, every tree, every snowflake, is somehow encoded on the surface of the glass sphere. If you had the right decoding key, you could reconstruct the entire interior from that flattened pattern alone. In the case of a black hole, the glass sphere is the event horizon, and the pattern is written not in paint, but in the quantum states of the horizon's surface. This concept, known as the holographic principle, takes inspiration from the way a real hologram works. A hologram is a two-dimensional piece of film that, when illuminated correctly, produces the illusion of a three-dimensional object. The wild suggestion here is that black holes operate in a similar fashion, except they are not producing illusions, they are preserving the full actual information of the three-dimensional objects that fell inside. Why would nature do this? The idea emerged partly as an escape route from the black hole information paradox. If all the data about what falls in is stored on the horizon, then even as the black hole evaporates via Hawking radiation, there is still a mechanism in principle for that information to leak back out. The information isn't truly lost, it's just encoded in a form that is unimaginably hard for us to read. The mathematics of black holes actually hints at this strange compression of reality. The amount of information a black hole can hold its entropy turns out to be proportional not to its volume as you might expect, but to the area of its event horizon. This discovery made by Jacob Bekenstein in the 1972nd and refined by Hawking was a shock to the physics community. It suggested that the horizon's surface is more fundamental to the storage of information than the space inside. This is where the metaphor of the black hole's skin becomes so powerful. Instead of imagining the horizon as a door to an unknown interior, picture it as the outer layer of a living organism, one that reacts to and records every encounter. Matter and energy might still pass inward, according to general relativity, but quantum mechanics demands that their informational shadow is trapped on the horizon. If this horizon storage hypothesis is true, then it forces us to rethink not only black holes, but the nature of the entire universe. Because if a three-dimensional volume's information can be fully described by data on its two-dimensional surface, then perhaps our whole cosmos, everything we see, touch, and experience, is itself a projection from a deeper, more fundamental layer of reality. In that case, we are all living inside the ultimate hologram. This is more than poetic speculation. Certain versions of string theory, one of the leading candidates for a theory that unites quantum mechanics with gravity, naturally incorporate holographic principles. In these models, the three-dimensional bulk of a region of space is mathematically equivalent to a two-dimensional boundary where the true physics is written. The event horizon of a black hole is simply the most dramatic and unavoidable example of such a boundary. The implications ripple outward into philosophy as well as physics. If reality itself is holographic, then what we perceive as depth might be an emergent illusion, much like the moving images on a cinema screen are not actually moving at all. And if that is the case, then the loss of information in a black hole is no longer a paradox. It's simply a transfer from one layer of the hologram to another. Critics, of course, point out that this idea, while elegant, is not yet confirmed. We cannot simply walk up to a black hole with a cosmic magnifying glass and read the information off its surface. The mathematics is compelling, but direct evidence remains elusive. Still, the concept has reshaped the way physicists think about space, time, and information. It has provided a possible bridge across the yawning gap between Einstein's gravity and the quantum rules of the microscopic world. And here's the truly mind-bending twist. If information is indeed stored on the horizon, then falling into a black hole might mean something entirely different than we imagine. From one perspective, the viewpoint of the infalling object, you plunge inward, unimpeded, until you meet your fate near the singularity. From another perspective, that of a distant observer, you never truly pass the horizon. Instead, you become part of the black hole's surface record, your essence smeared thin across the skin of space-time, never quite disappearing. Both perspectives could be equally valid, stitched together by the strange logic of relativity and quantum theory. If this duality is real, it changes the narrative of the black hole from one of devouring destruction to one of transformation. The event horizon becomes not a grave, but a ledger, a place where the universe keeps perfect account of its own history, no matter how violent or strange the events. And so we are left with a haunting image, the surface of a black hole, as a shimmering, invisible sheet, carrying the ghostly imprints of everything it has ever touched. It is not the abyss that swallows and forgets, but the archivist that remembers. And if this is true for black holes, it may also be true for the cosmos itself. A thought that leads naturally to an even bolder and stranger possibility. What if the depth you see, the space you move through the three-dimensional solidity of the world, is nothing more than an extraordinarily convincing projection? Imagine reaching out to touch a mountain and realizing at some unfathomable scale, it is no more solid than the flickering image on a cinema screen. This is the unsettling, almost heretical suggestion behind the holographic principle. The idea that our entire universe may be fundamentally two-dimensional, with the third dimension emerging as a kind of optical illusion. At its core, the holographic principle proposes something startlingly simple. Everything within a region of space Every particle, every force, every ripple of space-time can be fully described by information stored on the boundary of that region. Think of it as a kind of cosmic bookkeeping, where all the real data lives not in the interior but on a thin shell at the edge. The interior is just the elaborate unfolding of that information into the experience we call reality. If this still sounds abstract, picture holding a DVD in your hand. It is flat, shiny, and unassuming. Yet etched into its surface is the entirety of a 2-hour film, complete with characters, landscapes, and emotions that seem to occupy a fully 3-dimensional world. The film is not inside the disc in any literal sense. The disc simply encodes the data that, when interpreted by the right device, creates the illusion of depth, movement, and life. According to the holographic principle, our universe may work in the same way. The player is the fabric of space-time itself. The disc is the far-off boundary of the cosmos, and we are the story unfolding from its encoded patterns. This idea didn't emerge from science fiction, though it sounds like it could have. It grew out of the struggle to reconcile Einstein's general relativity with quantum mechanics, particularly in the context of black holes. The paradox of information loss in black holes suggested that nature cannot allow information to simply vanish. The mathematics led researchers to a radical conclusion: the maximum amount of information contained in any region is proportional not to its volume, but to its surface area. This strange proportionality hints that the surface holds the true record of reality, while the volume is just a clever projection. In the 1992nd theoretical physicist Juan Maldacena found a profound expression of this idea within string theory. He proposed a model in which a universe with gravity and 3 spatial dimensions could be perfectly equivalent to a different universe without gravity, but with only 2 spatial dimensions. This was not a metaphor, it was a precise mathematical duality. In this framework, the bulk 3-dimensional universe is nothing more than a holographic image of the 2-dimensional boundary universe. This is where the principle starts to feel almost mystical. If the holographic model is correct, then your body, your memories, the light from distant galaxies, and even the passage of time itself are emergent phenomena, side effects of deeper patterns inscribed on an invisible surface at the edge of reality. Every heartbeat, every planet's orbit, every supernova explosion is both a local event and a rearrangement of data on that boundary. We are living inside the projection like characters inside a film who can never step outside the screen to see the projector. And yet this is not an illusion in the sense of being fake. The experience of depth is real within the projection, just as the world of a hologram is real to an observer who interacts with it. The key difference is that what we think of as fundamental space-distance location may not be truly fundamental at all. The boundaries data is the bedrock, and space-time itself is a construct that emerges from it. The implications stretch far beyond black holes. If the holographic principle applies to the entire universe, then the cosmos as we perceive it, vast, expanding, filled with billions of galaxies, is simply the large-scale expression of patterns on a 2-dimensional cosmic boundary. That boundary could lie at the unimaginably distant edge of the observable universe, or it could be something more abstract, existing in a higher dimensional space we cannot directly perceive. For cosmologists, this perspective flips the usual way of thinking. Instead of asking what is happening in the middle of the universe, they might instead ask what patterns are being written on its surface. Instead of seeing gravity as a fundamental force pulling objects through a 3-dimensional volume, we might see it as the emergent effect of changes in the boundary's information. The holographic principle is not just a new lens on physics, it is an entirely different camera. But this raises questions as deep as the principle itself. If the universe is a projection, what is the projector? Is there a mechanism outside of space-time that casts the hologram we live in? Or is the projection simply a feature of reality's mathematics, needing no projector at all, the way a hologram can be generated purely by the interference of light waves? And if the boundary holds the data of everything, does it also hold the record of our future? Or is it constantly updating with each quantum decision made within the hologram? Some scientists caution against taking the principle too literally. It is possible, they argue, that the holographic model is simply a powerful computational tool, a way of translating certain kinds of problems into more tractable forms. Others believe it could be the most accurate description of reality ever proposed. If future experiments, perhaps probing the deep structure of space-time itself, reveal signs of holographic encoding, the philosophical shock will be immense. Because if the holographic principle is true, then we are not beings living in an infinite expanse of three-dimensional space. We are patterns. Patterns written on the ultimate cosmic film, playing out in a way that feels real, because within the rules of the projection, it is real. We are not the actors on the stage, we are the stage and the script, the scenery and the story all at once. And that leads to the most haunting thought of all. If everything is a projection, then the boundary that contains our universe holds the totality of existence, not just the material world, but every moment of consciousness, every whisper of thought, every dream, every fear, every joy. All of it is woven into that two-dimensional tapestry at the edge of everything. Which means that to truly understand the universe, we may one day have to stop looking outward into the depths of space and start looking sideways toward the surface where reality itself is written. Information never dies, it simply learns how to hide. That is the provocative heart of one of the boldest ideas in modern physics, a theory that stands at the crossroads of black hole science and quantum mechanics. To understand it, we must step inside a thought experiment that blends the ruthless logic of mathematics with the slippery nature of information itself. A journey into the idea that nothing, not even the crushing grip of a black hole, can truly erase the past. When Stephen Hawking first proposed that black holes emit a faint glow of thermal radiation, now called Hawking radiation, it sent shockwaves through the physics community. If black holes could radiate energy, they could eventually evaporate away entirely. But this radiation appeared to be purely random, carrying no trace of the information about what had fallen in. That was a disaster for quantum mechanics, which insists that information about a system's initial state can never be destroyed. It can be scrambled, dispersed, and hidden in ways that defy our senses, but it cannot vanish. Here is where the idea of maximal scrambling comes, in an almost poetic way, to describe the ultimate level of information mixing allowed by the laws of physics. Imagine pouring a vial of dark ink into the ocean. Within seconds, the swirls of black twist into delicate tendrils, blending with the water in patterns so intricate you could never hope to reverse them by hand. Within hours, the ink is so thoroughly mixed that no part of the ocean is entirely free of it, and yet not a single drop has truly disappeared. In the same way, proponents of this theory argue the information from anything swallowed by a black hole is not lost, but diffused into the Hawking radiation in patterns so complex they make the most elaborate human encryption look trivial. This information as a flow concept changes the way we picture black holes. Rather than a one-way shredder that annihilates everything it swallows, a black hole becomes a cosmic blender, churning information into an unrecognizable soup of quantum correlations. If you could, in principle, capture every single particle of Hawking radiation emitted over the entire lifetime of the black hole, and analyze it with infinite precision, you might reconstruct the original data. It would be like reassembling a book after it had been shredded, burned, and the ashes scattered in the wind. Theoretically possible, but so far beyond practical reach that it might as well be magic. One of the striking features of this idea is that it does not violate either of physics' great pillars. Quantum mechanics gets to keep its sacred law of information conservation, while general relativity still describes the graceful space-time warping geometry of black holes. The two theories do not so much compromise as reach a grudging détente, agreeing that the black hole's event horizon is not a place where information dies, but where it undergoes the ultimate transformation. Yet there is a darker edge to this reconciliation. If information is hidden in the Hawking radiation, then the horizon is not the smooth, serene boundary Einstein imagined. Instead, it may be a tangled quantum mess, a place where the very fabric of space-time is buzzing with chaotic activity. From a distance, the black hole still looks like a perfectly spherical void, but on the microscopic scale, its surface is alive, with the constant birth and annihilation of particle pairs, each carrying whispers of the information from the pairs of the two Martian objects that fell in long ago. For us here in the comparatively calm regions of the universe, this has staggering implications. It means that every photon of Hawking radiation is not merely heat, but a carrier of hidden history, the final encrypted record of something that once was. A star that collapsed a planet, swallowed whole, even a stray astronaut who crossed the point of no return. Their stories are not erased, but encoded in the faint, random-seeming glow. The black hole becomes a librarian with the most secretive archive imaginable, storing its volumes not on dusty shelves, but in streams of nearly featureless radiation drifting into the void. The challenge is that this library is effectively unopenable. The patterns are not just scrambled, they are maximally scrambled. In cryptography terms, they are locked behind the universe's strongest possible key. The idea is not that we lack the technology today, but that the very nature of the encoding ensures it would take longer than the age of the universe to decode. Still, in the strange, stubborn optimism of physics, impossible often means only not yet understood. If future theories or experiments were to reveal even a hint of structure in Hawking radiation, even a small deviation from perfect randomness, it would be the first crack in the door to this cosmic vault. It would tell us that black holes are not tombs for information, but vaults from which, with enough patience, data might one day be retrieved. In that moment, we would have to rethink not only the nature of black holes, but the ultimate fate of information in the cosmos. And so the image shifts. We no longer see the event horizon as the clean boundary of a silent giant. Instead, it becomes a membrane where two great theories, relativity and quantum mechanics, are locked in a delicate dance, where information does not fall into oblivion, but passes through a process so extreme that it emerges unrecognizable. It is still there somewhere in the radiation, streaming away, waiting for a mind clever enough, patient enough to untangle it. But this reinterpretation brings with it an unsettling corollary. If the event horizon is a place of such violent scrambling, could it also be something far more threatening than we have imagined? Could the horizon itself, in trying to preserve quantum information, become a lethal barrier, not a gentle, crossing into the unknown but a wall of fire? That question, whispered at the edges of theoretical physics, leads us into one of the most controversial and disturbing ideas about black holes yet proposed. Crossing the threshold of a black hole has always been portrayed as a strangely serene experience, at least in the equations of Einstein's general relativity. According to that elegant theory, if you were brave enough or unlucky enough to drift past the event horizon of a massive black hole, nothing remarkable would happen in that instant. You would feel no jolt, no shattering of atoms, just an unremarkable continuation of your fall into the abyss. The drama would be for outside observers, who would watch you slow to a crawl and fade into darkness. But in 2012, a startling idea shook this picture to its core. What if instead of a silent passage you were incinerated the instant you touched the horizon? This is the firewall paradox, and it lands like a punch in the face to Einstein's vision of spacetime. The proposal emerged from attempts to reconcile quantum mechanics' demands with the strange nature of black holes. The problem began with something that sounds deceptively harmless: entanglement. In quantum mechanics, particles can become linked in such a way that the state of one immediately tells you something about the state of the other, no matter how far apart they are. Hawking radiation relies on this phenomenon, with particles forming near the horizon and one escaping while its partner falls inward. For the radiation to be truly random, the escaping particles must be entangled with what's inside. But for information to escape and be conserved, those same particles must also be entangled with earlier radiation already far away from the black hole. Here's the catch. Quantum mechanics forbids a particle from being fully entangled with two different systems at once. This monogamy of entanglement forces a terrible choice. Either the escaping Hawking radiation is not connected to the interior, breaking the smooth fabric of space-time and creating a violent rupture at the horizon, or the rules of quantum mechanics are wrong. And very few physicists are willing to throw out quantum mechanics. So the firewall idea takes shape. Perhaps the event horizon is not a gentle gateway at all, but a sheet of unimaginably intense energy. Any matter, any person, any photon that tries to cross is instantly vaporized in a blaze hotter than anything in the known universe. The horizon becomes not a place of quiet transition, but the most lethal surface in existence. This is a shocking reversal for general relativity, which insists that a freely falling observer experiences nothing unusual at the horizon of a large black hole. To Einstein's equations spacetime there is smooth. To the firewall hypothesis, it is violently broken. If the latter is true, it means our two greatest theories, general relativity and quantum mechanics, are not just awkward roommates but mortal enemies when it comes to describing this region of the universe. The implications are unsettling. A firewall would mean that black holes are not passive vaults silently guarding their contents. They are active defenders surrounding their secrets with an invisible moat of pure destruction. In this view, information is not merely hidden and scrambled, it is guarded by the most extreme security system imaginable. No daring explorer, no clever alien probe could cross the horizon and report back, because the moment of crossing would also be the moment of annihilation. It also changes the way we imagine the nature of reality near a black hole. If space-time itself can fracture at the horizon, perhaps it is not the smooth, continuous fabric Einstein envisioned, but something granular, made of fundamental building blocks that can tear under extreme conditions. The firewall could be the visible scar of such a tear, the place where quantum laws override the smooth geometry of relativity. The paradox is still unresolved, and that is what makes it so haunting. There are physicists who argue that the firewall is an unavoidable consequence of trying to preserve both quantum mechanics and the principle of information conservation. Others insist that the firewall is a mathematical mirage, born from assumptions that will crumble once we have a true theory of quantum gravity. Still others propose exotic alternatives like soft hair on black holes or wormhole-like connections that would allow information to escape without invoking a wall of death. But even if the firewall turns out to be an illusion, its very existence as a hypothesis has forced physicists to confront the deepest contradictions in our understanding of nature. It has become a stress test for the foundations of physics, a place where our most trusted theories break down and demand something new to replace them. For anyone imagining the human experience of such an encounter, the scenario is brutally final. There is no slow descent into darkness, no time to send a farewell message, no eerie sensation of floating into the unknown. The crossing itself is the end, a flash of unimaginable heat and energy followed by nothing. If Einstein's vision is a cosmic lullaby, the firewall is a gunshot. And yet the mystery goes deeper still. Because beyond the horizon, whether guarded by a firewall or not, lies a realm where our concepts of space and time begin to dissolve. In that hidden interior, time may lose its meaning altogether, stretching and twisting until the word before and after no longer apply. That is where we must go next, into the heart of the black hole, where even the clock forgets how to tick. Near a black hole, time itself becomes a fragile, distorted thing. Imagine standing on the edge of its invisible boundary, feeling the pull of gravity so strong that it stretches not just your body but the very rhythm of your existence. To you, everything seems normal. Your heart beats, your thoughts flow, your body moves. But to anyone watching from far away, your life slows to an agonizing crawl. A single second for you could stretch into thousands of years for them. From their perspective, you are frozen in place, caught forever in the moment before you cross the event horizon. This is the mind-bending effect of gravitational time dilation predicted by Einstein's theory of general relativity. It tells us that time is not absolute, not a universal metronome ticking identically for everyone everywhere. Instead, it is elastic, bending and twisting under the influence of gravity, the The stronger the gravitational field, the slower time flows. And near a black hole, gravity reaches its most extreme bending time, almost to the point of stopping. To an outside observer, you would never actually vanish beyond the horizon. You would just fade your image redshifting into deeper and deeper hues until it disappeared into blackness. But from your own perspective, you would cross the horizon without noticing anything unusual, unless, of course, the firewall hypothesis is correct, in which case your story ends rather more abruptly. Still assuming the horizon is smooth, your subjective clock keeps ticking as normal, while the rest of the universe races ahead without you. This leads to one of the most haunting scenarios in all of physics. If you linger near a black hole's edge, you could watch the universe evolve at a terrifying pace. Stars would flare, and galaxies would drift apart. Entire epochs would pass in what feels like moments. Civilizations could rise and fall while you are still taking your next breath. In principle, you could travel into the far future simply by hovering near the event horizon, though the practicalities of surviving such a place are another matter entirely. Philosophers have a name for the deeper implication of this phenomenon: the eternal death. It is the idea that you could be trapped between a single moment and all of eternity, unable to move forward in any meaningful sense. From the outside, you would be frozen. From the inside, you would feel time flowing, but the universe beyond would be slipping ever farther away, until the gap between your moment and the rest of existence became infinite. And if you actually cross the horizon, the nature of time becomes even stranger. Inside a black hole, the roles of space and time effectively switch. Moving toward the singularity is as inevitable as moving toward the future. It is not something you can choose to avoid. In the same way you cannot decide to stop tomorrow from arriving, you cannot stop yourself from falling inward. Time as you understand it is no longer the ruler of events. Instead, the very geometry of space-time forces you toward a final point where the known laws of physics fail. From a certain point of view, it is not just that time slows near a black hole, but that it begins to lose its meaning altogether. Outside time is a measure of change, a way to order events from past to future. Near the horizon, that order begins to fray. Inside, it collapses entirely. The question, what happens next, no longer makes sense, because there is no next. There is only the inevitable convergence on the singularity. This is why black holes feel so fundamentally alien to our experience. They are not simply exotic objects in space, but places where the very scaffolding of reality bends into shapes that defy our intuitions. To understand them is to confront the possibility that time, the thing we live inside every day, the thing that seems to carry us along like a river, is not as solid as we imagine. In extreme conditions, it can stretch, freeze, and finally dissolve. From a human perspective, this is both terrifying and oddly liberating. Terrifying because it suggests that our experience of time is fragile, dependent on the conditions we inhabit, and vulnerable to being torn apart. Liberating because it shows that time is not a prison we are trapped in, but a landscape that can be warped, navigated, and perhaps even escaped. But the reality inside a black hole remains hidden from us. No signal can escape from beyond the event horizon to tell us what it feels like to watch time unravel completely. We can only follow the mathematics, and the mathematics points toward a place where time as we know it ceases to exist. Beyond that, we are left with only speculation, and the uneasy feeling that somewhere in the universe there are regions where the clock simply stops. And if time can stop, if it can dissolve entirely in the depths of a black hole, then perhaps it is not the fundamental backdrop of the universe we think it is. Perhaps time is an emergent illusion, a pattern that arises only in certain conditions. Remove those conditions, and the illusion shatters. That possibility takes us to a question even stranger than the fate of matter in a black hole. What if time itself is not a basic part of reality at all? There is a place in the universe where every law of physics we know, every equation, every principle, every neat little model we have built to explain reality simply gives up. This is the singularity, the beating heart of a black hole, and it is unlike any other place we can imagine. Here density becomes infinite, space-time curves in on itself without limit, and our best theories collapse into a mess of infinities and undefined values. In the mathematical sense, the singularity is not just strange, it is undefined, like dividing by zero in a cosmic equation. At its core, the singularity is where general relativity and quantum mechanics, the two towering pillars of modern physics, both fail to describe what is going on. Einstein's equations tell us gravity crushes matter into an infinitely small point, while quantum theory insists that nature cannot allow such infinities to exist without some deeper structure beneath. The result is a deadlock. Our tools break, our models stall, and we are left with a place that exists in theory but cannot be fully described in language or mathematics. If you imagine the singularity as a physical point, you are already off track. It is not a speck of matter in space. In fact, the concept of space itself loses meaning here. Distances become irrelevant because the geometry of space-time has been twisted so violently that inside the black hole, all possible paths lead inevitably toward the singularity. You cannot orbit it, you cannot escape it, and you cannot pause beside it to take a closer look. It is the ultimate one-way trip. The most unsettling part is that we have no idea what actually happens to the matter and energy that fall into this abyss. Does it get crushed into an infinitely dense state? Is it transformed into some exotic form of existence that our minds cannot yet grasp? Or does it simply vanish, erased from reality itself? If information is truly destroyed at the singularity, that would be a direct violation of one of the deepest principles in physics, the principle of unitarity, which says that information can be scrambled and hidden, but never lost entirely. Some physicists have suggested that maybe the singularity is not the end of the story, but rather a doorway to something else. In certain speculative models, the collapse inside a black hole could bounce in some manner, creating a new expanding region of space-time, in other words, a baby universe. In this picture, the singularity is not a point of annihilation, but a point of birth, the seed of a cosmos entirely separate from our own. If this is true, every black hole could be a womb for new universes, each with its own physical laws, its own timeline, perhaps even its own versions of stars, planets, and life. But there is no way to test this idea directly. The singularity is hidden behind the event horizon, and the event horizon is a wall no information can cross back through. Anything we learn about the inside of a black hole must come from indirect reasoning from the patterns we observe in the light and matter outside, or from the predictions of our incomplete theories. This makes the singularity one of the most frustrating mysteries in science. We know it exists mathematically, we suspect it exists physically, but we cannot reach it or see it. Philosophically, the singularity is a mirror held up to our ignorance. It shows us the boundaries of human knowledge, with a kind of cruel precision, reminding us that even our most advanced science has edges beyond which we are blind. For centuries, physics has been about pushing those edges farther out, turning the unknown into the known. The singularity resists that process. It stands like a cliff at the end of our intellectual map where all the paths just stop. And yet there is something thrilling in that. To confront the singularity is to be reminded that the universe still has places both in space and in concept that remain untouched by understanding. It is a challenge, a provocation, an invitation to imagine new physics that might reconcile the clash between relativity and quantum mechanics. Perhaps the true nature of the singularity will only be revealed when we have a complete theory of quantum gravity, something that unites the smooth fabric of space-time with the jittery granularity of the quantum world. Until then, we can only speculate. Maybe inside the singularity information is encoded in ways so alien to us that our current ideas of data and storage are meaningless. Perhaps the contents of a black hole are smeared across the fabric of the cosmos in ways we have yet to detect. Or perhaps in the most radical scenario, the singularity is not a place at all, but a transition, a change in the very nature of reality. In any case, the singularity forces us to grapple with the possibility that the end might not be an absolute annihilation. It could be a threshold, a boundary between one kind of existence and another. And if that is true, then what looks to us like the death of matter, energy, and information might actually be the birth of something new. Something that for now remains hidden behind the most impenetrable veil in the universe. Which raises a tantalizing question. What if this end is not the final chapter, but the first sentence of a completely different story? Every black hole you see glittering in the cosmic night sky might be hiding the seed of an entirely new reality. The idea sounds like pure science fiction, but in some corners of theoretical physics it is considered a serious possibility. Imagine this: instead of being the ultimate dead end, the singularity at a black hole's core could be a passageway, a cosmic chrysalis, where the collapse of matter in one universe becomes the birth of another. From our perspective, the black hole swallows light, time, and matter. From the inside of this hypothetical newborn universe, that moment could be remembered, if it is remembered at all, as a sudden and cataclysmic beginning, a Big Bang. This concept emerges from an intriguing problem in physics. If information truly cannot be destroyed, then it must go somewhere when it crosses the event horizon. The standard picture says that matter falls inward, space-time curves infinitely, and the singularity marks the end of the story. But certain solutions to Einstein's equations hint that the singularity may be more of a gateway than a grave. Under extreme conditions, space-time itself could bounce instead of collapsing to nothing, expanding outward into a completely separate continuum, one that is causally disconnected from our own. If this is the case, then the universe we inhabit could itself be the offspring of another universe's black hole. Somewhere long before our cosmic clock began ticking, matter in a different realm might have collapsed past an event horizon, undergone this bounce, and emerged as our Big Bang. In this sense, black holes would not be rare monsters, but reproductive organs of the cosmos, each capable of spawning its own independent creation. Inside such a baby universe, the physical laws might be slightly different from ours. The values of fundamental constants, the speed of light, the strength of gravity, the charge of the electron could vary just enough to produce a different cosmic story. In some, stars might form faster, galaxies might cluster more tightly, and life might never arise. In others, conditions might be far more favorable than in our own reality. This idea has even been tied to a strange evolutionary logic called cosmological natural selection, where universes that produce more black holes end up creating more offspring, and thus more universes like them. If this picture is true, then nothing that falls into a black hole is truly lost. Every atom, every photon, every piece of information would be carried into a new cosmic environment, not destroyed, but transformed. What looks to us like an ending, the last scream of light before the event horizon, might, from another perspective, be the opening note of an entirely new symphony. In that sense, black holes would be both tombs and wombs, endings and beginnings wrapped into one. Yet there is a deeply frustrating problem with this hypothesis. It is almost impossible to test. The event horizon cuts us off from whatever lies beyond. Even if a black hole does give birth to a new universe, we have no direct way to observe it from the outside. No signal, no flash, no ripple in space-time is expected to return from that hidden realm. From our perspective, it is a perfectly sealed vault. Still, physicists are clever. Some suggest that subtle patterns in the radiation or gravitational waves emitted as a black hole forms might carry indirect clues about what is happening inside. Others look to the mathematics of quantum gravity, the long-sought theory that would merge general relativity and quantum mechanics, hoping that a complete set of equations will naturally predict universe creation as a consequence of collapse. A few even speculate that the initial conditions of our own universe might hold the fingerprints of the black hole that birthed us written into the cosmic microwave background, or the large-scale structure of galaxies. The philosophical implications of this idea are staggering. If black holes create universes, then the cosmos is not a static one-time event, but a living, branching tree of realities. Every universe could be a child of another, stretching back into an endless genealogical chain, or perhaps a tangled web of cosmic ancestry. In that case, the question, where did it all begin, becomes far more complex. There may have been no single beginning, only an infinite process of birth and death, collapse and expansion echoing across realities. And then there is the unsettling possibility that some universes might remember their parents in subtle ways. Not consciously, of course, but through inherited properties, the curvature of space-time, the spectrum of particles, the balance between forces. Just as life evolves, traits over generations, perhaps universes do too, driven, not by natural selection in the biological sense, but by the physics of black hole reproduction. For now, this remains speculation, elegant and mind-bending, but unproven. The closest we can come is to follow the mathematics wherever it leads, to design experiments that might test the edges of these ideas, and to embrace the fact that some of the universe's most profound truths may remain hidden forever. It is a strange feeling to know that a black hole could be cradling an entire reality within it, yet to be utterly powerless to peer inside. But perhaps that is part of the beauty. The idea that our universe itself might be the child of a long-forgotten star's collapse is a reminder that endings can be beginnings, that death in the cosmic sense might be nothing more than a transformation. The night sky could be full of pregnant silences, each black hole, a secret story in progress, each one holding the possibility of worlds that will never know ours existed. And if that is true, then the universe is far more alive than we ever imagined. Which leaves us with the haunting question: if every black hole is a birth, how many universes are being born right now, in the silent darkness beyond our reach? The universe does not always speak in light. Sometimes it whispers in the language of gravity itself, sending ripples through the very fabric of space-time. These ripples, called gravitational waves, were predicted over a century ago by Einstein, but for decades they remained purely theoretical, too faint for our instruments to detect. That changed in 2015 when scientists at LIGO, the Laser Interferometer Gravitational Wave Observatory, picked up a signal from over 1 billion light-years away. Two black holes had collided their final dance, shaking the universe so violently that the disturbance traveled across cosmic distances to gently nudge the mirrors of our detectors here on Earth. That nudge, smaller than a fraction of a proton's width, was the sound of the cosmos itself, a deep, resonant chirp, marking the death of two black holes and the birth of one. This was more than just a confirmation of Einstein's vision. It was the opening of an entirely new sense for humanity, the ability to hear the universe instead of only seeing it. Light can be absorbed, scattered, or blocked, but gravitational waves pass through matter almost untouched, carrying pristine information about the most violent events in the cosmos. And for black holes, which emit no light of their own gravitational waves, are often the only direct signal they send into the void. When two black holes spiral into each other, their immense masses warp space-time, creating waves that stretch and squeeze the universe as they propagate outward. The shape of these waves encodes a detailed fingerprint of the event, the masses of the black holes, the speed of their rotation, even the moment they merge. But some physicists suspect there could be more hiding in the data, something far stranger. They wonder if subtle irregularities in the waves could reveal hints about what really happens at or inside the event horizon. Here's the idea. If the smooth, perfect picture of a black hole that Einstein described is incomplete, then the collision of two such objects might reveal its flaws. Perhaps the horizon is not perfectly silent, but instead rings with faint echoes after the merger. These echoes could be caused by exotic structures just outside the horizon, or by new physics that allows tiny amounts of information to escape. Detecting such echoes would be like hearing a whispered secret beneath the roar of a cosmic explosion. Incredibly difficult, but not impossible, with the right tools and enough patience. If those hints could be found, it would revolutionize our understanding of black holes. For decades, the information paradox has haunted physicists, pitting the rules of quantum mechanics against the predictions of general relativity. If gravitational waves could carry even the faintest trace of information from beyond the event horizon, it would mean that black holes are not the one-way traps we thought they were. Instead, they might be leaky vaults, bleeding clues into the universe with every collision. Gravitational wave astronomy is still in its infancy, but it is advancing at astonishing speed. The first detection in 2015 was followed by dozens more in just a few years. Mergers between black holes, between neutron stars, and even between a black hole and a neutron star have all been recorded, each event expanding the library of cosmic sounds we can analyze. With every detection, algorithms sift through the data, searching for patterns that shouldn't be there, anything that could hint at a violation of the clean, classical picture of black holes. Future detectors will be even more sensitive. Projects like the Einstein Telescope in Europe and Cosmic Explorer in the United States aim to hear gravitational waves from across nearly the entire observable universe. And then there's LISA, the Laser Interferometer Space Antenna, a fleet of spacecraft planned by the European Space Agency that will drift millions of kilometers apart in space, detecting low-frequency gravitational waves from massive black hole mergers that ground-based instruments can't hear. These next-generation observatories may give us the resolution and precision needed to pick out those faint hypothetical echoes from the noise. If that day comes, it will be one of the most profound moments in the history of science. To hear a gravitational wave is already to touch an event billions of years and light years away, but to extract hidden information from it would be to open a channel of communication with a realm we have never entered. It would mean that the horizon is not an absolute wall, that the secrets of what lies beyond might not be locked away forever. Even if no echoes are ever found, gravitational waves are still priceless. They are the ultimate messengers from the most extreme corners of the universe, carrying not just the story of black holes, but of neutron stars, supernovae, and perhaps even the very first moments after the Big Bang. In a sense, they are the heartbeat of the cosmos, pulsing quietly through space-time, waiting for us to listen closely enough to understand. And yet there is something almost eerie about them. When LIGO detects a signal, scientists sometimes play it as sound compressing billions of years of travel into a fraction of a second. The result is often just a short, rising whoop, simple, unassuming, almost gentle. But to think that such a sound represents the death spiral of objects more massive than entire star systems is to realize how alien the universe truly is. The waves carry no light, no image, no color, only motion itself stretching and squeezing space like a silent tide. Somewhere out there, even now, black holes are colliding, their gravitational voices rippling outward in all directions. Some of those waves may pass through us tomorrow, next week, or in 1,000 years. We may not yet have the technology to decode every nuance they carry, but we are learning step by step to listen. And one day, if the whispers of the universe truly carry the secrets of black holes, we may finally hear them clearly. Until then, gravitational waves remain our most tantalizing hint, the faint tremors of cosmic cataclysms, the subtle shivers of space-time that remind us the universe is not silent at all. It is speaking. We are just learning its language. And perhaps hidden in that language lies the key to unlocking the deepest mysteries of the black hole. The most unsettling thing about the universe is not necessarily what it hides, but what it reveals, truths so alien to human thought that even glimpsing them feels like staring directly into madness. In cosmic horror, this is the heart of the fear. The monster is never just the creature in the shadows. It is the realization that the rules you thought governed reality are flimsy and local, that your mind is not built to comprehend what truly lies beyond. You can run from a predator, you can fight an invader, but you cannot defend yourself from an idea that unravels the very structure of your understanding. Black holes are the perfect embodiment of this philosophy. They are not malicious, they are not plotting, they are not even aware of you. They simply exist, operating according to laws that feel like they belong to another universe entirely. Their event horizons are like the locked covers of a book written in a language no one can read yet. You know, the text inside is fundamental to the story of everything. You can stand outside forever circling the mystery, but you will never read the pages. And the more you learn about what might be in there, the more the edges of your comprehension begin to fray. Part of what makes them terrifying is their complete indifference. The sun blazes with a kind of generosity, pouring energy outward, bathing worlds in light and warmth. A supernova, even in its violence, is a kind of spectacle, a display that illuminates the cosmos. But a black hole offers no such generosity. It gives nothing back. It takes it, conceals, and it closes over what it swallows. Whether you are a speck of dust or an entire galaxy's worth of stars, the black hole does not care. You are simply fuel for its gravity, another detail in its private, unknowable ledger. Then comes the question that gnaws at physicists and philosophers alike. What happens to information once it crosses that horizon? In physics, information is not just data in a computer or memories in your brain. It is the total set of details that describe the state of matter and energy, everything from the position of a particle to the chemical composition of a star. According to the rules of quantum mechanics, information cannot be destroyed. But according to classical descriptions of black holes, once something falls in, it is gone forever, leaving no trace. This is the infamous information paradox, a puzzle that sits like a splinter in the fabric of modern science. If information is truly lost, it would mean that the universe is not a consistent ledger but a corrupted one, that history itself can be erased. The implications are staggering. It would suggest that the deepest laws we thought were unbreakable, the conservation of information, can fail. Reality would have loopholes big enough to swallow not just matter but truth. From a human perspective, that is almost more frightening than death itself, because it is not just you that disappears but the fact that you ever existed at all. If, on the other hand, the information is preserved, somehow hidden, scrambled, or transferred elsewhere, then the horror changes shape. Now, it is not about loss, but about inaccessibility. The truth exists, but it is locked away beyond your reach, like a sealed vault whose combination is written in the language of a higher dimension. You might spend centuries building machines, decoding theories, probing the edges of the horizon, and still be no closer to opening it. This is the flavor of cosmic horror, where the villain is not destruction, but the eternal reminder of your own limits. The unease deepens when you realize that this is not just a poetic metaphor. Black holes actually warp reality so profoundly that time, space, and causality, the scaffolding of our understanding, all buckle near them. You are used to thinking of before and after as fixed concepts, but near an event horizon, those concepts can stretch, twist, or even flip. The very coordinates of existence lose their stability. It is like discovering that the floor beneath you was never solid, just a temporary agreement between forces that are now unraveling. Cosmic horror thrives on these moments when the familiar collapses under the weight of the incomprehensible. It is the same chill you might feel when contemplating infinity, or when realizing the Earth is a tiny speck drifting through a vast, uncaring void. Black holes take that feeling and sharpen it into something tangible, something with a gravitational pull so strong it could tear you apart, atom by atom. They are the physical manifestation of the phrase "you were never meant to know." And yet humanity keeps trying. We aim telescopes at the shadows of black holes, we model their interiors on supercomputers, we dream up wild theories about wormholes, baby universes, and quantum firewalls. Part of us wants to believe that with enough persistence, enough genius, we could crack the code. But there is an equally strong part, the part steeped in cosmic horror, that suspects we will never succeed. Not because we are not clever enough, but because our minds, forged in the gentle physics of Earth, are not built to process what black holes truly are. That is the real horror, the suspicion that some truths will remain forever outside our reach. That there are answers sitting in the universe right now, as concrete and real as the ground beneath your feet, but your brain, any brain, will never be able to grasp them. The black hole does not need to threaten you. It simply needs to exist, and you will supply the fear yourself. Still, we cannot look away. Even in horror there is fascination. We are drawn to the event horizon, the way a moth is drawn to a flame, knowing it will destroy us but unable to resist the pull of its mystery. We write equations like incantations, hoping to summon some understanding, and we stare into the simulated images of these cosmic abysses, searching for meaning in the darkness. And somewhere in that darkness perhaps lies the most chilling possibility of all, that one day the barrier will fail. That whatever secrets are locked inside a black hole will find a way out, not in whispers of gravitational waves, but in something more direct, more undeniable. And when they do, the universe will not necessarily become more comprehensible. It may only become more alien, more unsettling, more strange than we ever dared to imagine. If the universe truly keeps every story, then somewhere etched into the invisible threads of space and time, yours is already written. Every moment you have lived, every choice you have made, every word you have spoken, they are not drifting into nothingness. They are stored, recorded in a cosmic archive so complete that nothing is ever truly gone. This is not poetry, but the logical conclusion of a universe where information cannot be destroyed. And if one day we could prove that even black holes, those ultimate vaults of secrecy, eventually release what they take in, then the implications would ripple through our understanding of reality, history, and ourselves. Imagine standing at the edge of such a revelation. For centuries, black holes have been symbols of erasure, the final full stop at the end of existence. To learn that nothing is truly lost, that every photon, every vibration, every flicker of thought survives in some form, is to replace the fear of oblivion with something far stranger. Oblivion, at least, offers a clean break. But immortality, the immortality of data, means that everything you are and everything you have done is woven permanently into the fabric of the universe. At first it sounds comforting. The loved ones you miss, the fleeting moments you wish you could hold on to, the experiences you fear will fade. They are not gone, not really. Somewhere in ways we cannot yet access, they still exist. You could imagine the universe itself as an infinite memory holding all the laughter and tears of every living thing. There is a tenderness in that idea, a cosmic reassurance that nothing is ever truly forgotten. But think deeper, and a different kind of fear emerges. If nothing is lost, then the mistakes remain too. Every harsh word, every betrayal, every shameful impulse you have ever had, preserved alongside your triumphs. There is no erasing them, no matter how much you grow, no matter how much you regret. They become part of your eternal record, immutable, waiting in the structure of space-time like fossilized truths. The universe does not edit your story, it keeps it all. And it is not just about the personal. This would mean that the horrors of history, the wars, the atrocities, the moments of cruelty and indifference are all still there, perfectly recorded. We may choose not to dwell on them, but the cosmos does not choose. It does not forgive, it does not condemn, it simply remembers. That is its nature. If black holes release information, they are not erasing the dark chapters, they are preserving them alongside the bright ones. The philosophical weight of such a truth is enormous. It forces a shift in how we see morality, legacy, and even free will. If every action is permanent, does that change the way we live? Should it? Would knowing that your life's every detail was being woven into the eternal tapestry inspire you to live with more care, or paralyze you with the knowledge that perfection is impossible? Would it make you more honest or more cautious? Science often changes us by expanding our horizons, but sometimes it changes us by deepening the shadows. The discovery that nothing is lost would be such a moment. We would have to live with the certainty that we can never truly hide from ourselves, that somewhere in the vast ledger of existence, our story is complete and unalterable. In practical terms, this would reshape physics too. It would mean that reality has a kind of built-in backup system, a redundancy that prevents any piece of it from being erased. In a way, the universe would resemble a perfect book, one that cannot be burned, rewritten, or censored. The pages may be scattered, folded into dimensions we cannot yet see, but they remain intact. Scientists would chase these hidden records, not to invade privacy, but to understand the structure of reality itself. What would it mean if one day we could actually retrieve them, reconstructing moments from billions of years ago? Would we look upon our ancient ancestors, the birth of the stars, the first stirrings of life? Or would we stumble upon things we were never meant to see? And then there is the personal question, the one that lingers after the equations are done. If your story will last forever, what story are you telling? Are you living as if your actions are being etched into eternity? Or do you live as if they vanish when the moment passes? The idea that nothing is lost is a challenge, not a comfort. It dares you to be intentional, to live with the awareness that every choice matters because it will never be erased. Of course, there is another way to see it. Perhaps it is freeing. If the universe remembers everything, then you can stop trying to hold on so tightly. You do not have to be the guardian of your past because it is already safe whether you want it or not. The burden of memory is lifted from you and placed on the shoulders of space-time itself. You are free to keep moving forward to create new chapters, knowing that the old ones are beyond your power to change or to lose. And yet in the quiet moments, the weight of that permanence might still press on you. We are creatures of forgetting as much as remembering. Forgetting allows us to heal, to let go, to reinvent ourselves. If forgetting is impossible, then we must learn a new way to make peace with the past. We must live not by erasing our mistakes, but by outgrowing them until they are part of a larger pattern that defines us without trapping us. If one day the secrets of black holes escape their darkness, they will not just change our textbooks, they will change our relationship with time, memory, and meaning itself. We will look into the night sky knowing that it is not empty, that it is full of stories, every story written into its structure. And somewhere among them is yours, unchangeable, enduring, waiting to be read. So the final question is not whether the universe keeps your story. It does. The question is whether you want it to shine forever in the cosmic record or to lie quietly in the deepest, oldest shadows, not lost but hidden, where perhaps no one, not even you, will ever find it again.